Good morning. Okay, can you all hear me? Can you see my screen?
Yes.
Thank you. Okay, so we're looking at module 11 today. Well, let's take a look at this schedule here, see where we're at. Okay, so yes, we're on, this is the 28th today. We are looking at module 11. So Wednesday we'll look at module 12. Next Monday I'll be doing review.
They said the insurance company would probably recommend a repair.
And we'll look at, you'll look at doing test 2 on the Wednesday of next week. Okay, so you've got plenty of time to go over everything you need to go over here, I think. And the review session, I'll be going over the sample test, which is going to be identical to the test. Well, it's going to be the same kind of formatting and everything as the test you'll be taking on by that Wednesday. Remember, you don't have to wait till Wednesday to take that test. You can take it any time up to that point. All the homework will be due on the night before that test. That's next Tuesday. So you've got a week to get all the homework done. And there are some relatively time-consuming exercises that need to be done for this one if you want to get the homework done. Remember that it's the same situation as it was in test 1. If you do all of the, if you do the sample test, you get 80%, then you'll be able to get 5% extra credit that will be added to your test score. So that's certainly worth doing. I think, again, only half people did it for test 1. I think you need to do it for test 2. I think it's a good idea. It needs to be done by the night before the test as well if you want to get that extra 5%. Okay, does anybody have any questions about the schedule and what we're doing here? Okay, so going back, we're looking at module 11 here. Okay. I'm going to ask that you all mute, please, if you can. I can make you mute, I guess, but I would rather you mute yourselves, especially if you're going to be making noises. All right. So I'm going to ask that you read the stuff here in the background. We're going to be dealing with this equation a lot here. P1V1 over T1 equals P2V2 over T2, which is called the combined gas law because it combines the concepts of pressure, volume, and temperature. The fact that it's P1V1 equals P2V2, just ignoring the temperatures here, indicates that we're dealing with what is called an inverse relationship, meaning as pressure goes up, volume goes down. And that's always the case when you've got things being multiplied on each side here, P1V1 equals P2V2. Now, if you look at the pressure and temperature, you can see that that's going to be a direct relationship. P1 over T1 equals P2 over T2. Also, volume over temperature is a direct relationship. Now, all of this makes sense because when you've got a balloon and you put pressure on it, you would expect the volume of the balloon to decrease. So that would be an example of P and V. Volume and temperature, when you put a balloon on a hot surface, you'd expect that balloon to expand. So the hotter something gets, the volume increases. Also, the pressure inside the balloon would increase as well. So those are all examples of what we're talking about with inverse and direct relationships as they relate to the combined gas law equation. Now, these are all based upon what we call ideal gases, and ideal gases aren't real gases, of course, but they will, the equation will best suit gases that have certain or obey certain assumptions. And those assumptions are that the volume taken up by gas molecules is zero. All collisions are perfectly elastic. What that means is that if you throw a ball against a wall, usually it loses energy as it hits the wall. We're assuming that those molecules don't do that. And the other thing is we're assuming the molecules don't attract or repel each other, which is usually not the case either. So the main thing I want to want you to get out of this is that there's certain consequences that come from these assumptions, and that is that small molecules move faster than large molecules. That's going to be important for a question type you might see on the test, and I'll show you some examples of those in a minute, or an example in a minute. And the rest of it here, STP, standard temperature and pressure, 1 atmosphere is 760 millimeters of mercury, and at 273 Kelvin. 1 millimeter of mercury is equal to 1 torr. So that's a common unit that we'll see throughout module 11. Both of those things mean the same thing. 1 mole of any gas occupies 22.414 liters at STP, and that's a relationship that we've been using a lot throughout module 9, and I think module 7 as well. So I talked about Boyle's law, Charles' law, and the combined gas law. The other thing we'll be looking at will be the ideal gas law, which is PV equals nRT. Let me see what this is here. Here we go. So here's a kind of a similar question as to what you get on the test, where you'll have to order certain molecules and from fastest to slowest. Now, what I was saying earlier was that when you look at the molecules, the heaviest molecules move slowest. So the ones that move fastest will be the lightest ones. How do we get the lightest ones? Well, we just look at the weights. So you look at helium. Helium is 4. Nitrogen, N2, would be 28. Oxygen, O2, would be 32. AR, I think it's like 40. And Cl2 is something like 70 something, 71, something like that. So what you do is you order them here. It says from fastest to slowest. So the fastest one would be helium because it's the smallest. And then you just put them in order as they appear. So I think Cl2 would be the heaviest one. So I go down here, and N2 would be here, O2, and then AR would be here. So that's the kind of question that you'd be expected to answer on the test as well. It won't be quite like that. It won't be drag and drop, but you know, you'll have to put in numbers and order them that way. But that's how you order them. Does anybody have any questions? So the other kind of question you might see will allow you to determine the molecular weight of a compound using this relationship here. 1 mole is equal to 22.414 liters. The other thing we would need would be the density of the gas as well. So a density of any gas is going to be its molecular weight divided by the molar volume at STP. Now the molar volume at STP is at 22.414 liters. So if you had something that will say like methane that has a molecular weight of 16.04 grams per mole, then we could divide that effectively by the molar volume, which means times 1 mole over 22.414 liters. That allows the moles to cancel, and we'd be left with a density of grams per liter. So you're usually used to using grams per milliliter as a density unit. And the reason you might do that is because we're usually dealing with solids and liquids. And when we're looking at solids and liquids, it often turns out that they're much denser than gases. So gases, being not very dense, will usually be measured as grams per liter. But that's the relationship we're looking at here. Density is equal to molecular weight divided by molar volume. We can rearrange this a little bit. And by rearrange, what I'm talking about is that we can find the molecular weight of something if we have the density of the gas at STP. So all we would have to do then is take the density, which is 2.00 grams per liter in this case, and simply multiply it by the 22.414 liters. You can see the liters will end up cancelling. We'll end up with 44.8 grams per mole. So that would be the molecular weight of the gas. And so this is actually a viable way to measure the molecular weight of a gas. You can take the temperature down to 0 degrees Celsius. You can make sure you've got 1 liter of it, and you can measure its density, and you could possibly figure out the molecular weight of that gas. On the test, the kind of problem you might see might relate to something like this, where it says here, which molecule has a density of 3.16 grams per liter at STP. So what you would do in this case is do what we did in the problem here, take the 3.16 and multiply it by 22.414. And that comes out to be 70.8. So I think the answer here is going to be Cl2. And the reason I say that is because that's the one that matches that specific molecular weight. So you may have to do a little bit of trial and error, figure out some molecular weights of these, but whatever one matches whatever you get from this equation will be the answer to that problem. So on the test, the two possibilities for one of the problems is going to be the ordering of those velocities that I showed you earlier, or possibly figuring out the identity of a gas based on simply having a density. Does anybody have any questions so far? Okay. All right, let me pull up my paintbrush here. Ooh, let's get rid of some of this stuff here. Okay. So the first foray into gas equations that we'll be looking at will be using Dalton's law of partial pressures, which basically states that the total pressure of any system that involves gases is simply the pressure. The total pressure is always going to be the sum of all the pressures of all the gases, which I think makes a great deal of sense. So P total is PA plus PB plus PC, whatever those gases happen to be, but this only applies to gases, of course. So let's say you've got a situation, and this is a fairly common thing that we'll see here. So you've got a container, and this would be a pressure gauge attached to that container. And this will measure, this will measure P total. Now in this container, we might have water. And the water is, I'm going to represent it with little circles here. And then we could also have a gas, which I'm calling X. But what's going to happen is we're going to have X in the container. And what I'm saying is it's over water. Now, what we know about water is that it doesn't appear just in liquid form. When it's in any container, there's always going to be a small amount of water floating around above the water liquid itself. So the total, the P total here, is going to equal the P of gas which I'm going to call X, plus the P, and I'll just write water here, plus the pressure due to water. So if we have the P total, and we would, because we would have this reading of the pressure gauge here, then we can also find the pressure of water using a table, which I'll show you in a second. That means that we can solve for the pressure of the gas, or the partial pressure of the gas, as we call it. So this is from a table. So let's have a look at that vapor pressure table. So this is it here. So this applies, it doesn't matter how much water you've got in the bottom of a container. This will always be the vapor pressure of water, and it's related to whatever the temperature happens to be. So you can see at very low temperatures, the vapor pressure is very small. So we've got, say, even at 0 degrees Celsius, it's 4.6 millimeters of mercury, which is not very high. You'll notice that as we approach 100 degrees, though, the vapor pressure increases. And then at 100 degrees, that's 760 millimeters of mercury, which is 1 atmosphere. 100 degrees, of course, is the boiling point of water. So this is another definition. It's actually the correct definition of boiling point, is the temperature at which the vapor pressure of a liquid equals atmospheric pressure. And whatever temperature that is, that happens to be the boiling point. And we already know it's 100 degrees Celsius for water. So we're usually dealing with temperatures in this range from 22 up to 40. And you can see the vapor pressures slowly go up as the temperature goes up, which makes a great deal of sense, I think, because if we're going to have water in here and we're heating it, we're expecting more water to be above the surface of the liquid water the higher the temperature goes. So going back to the problem here, it says a sample of gas is collected over water. The total pressure reads 790 millimeters of mercury. So that would be the P total, whatever's on the pressure gauge. We're also given the temperature, and that's at 27 degrees Celsius. We're looking for the partial pressure of the gas. So what we do is we go down to the table, we look up 27 degrees Celsius. It comes out to be 26.7 millimeters of mercury. It says, I think it's got the units here, millimeters of mercury underneath, yeah. So you can see that if we've got P total is equal to P gas plus P water, then P gas is just going to be P total minus P water. You'll notice that since this is subtraction, it goes by number of places past the decimal, which means we end up with 763 millimeters of mercury as the partial pressure of the gas. Does anybody have any questions about using that sheet, the vapor pressure of water chart here? Okay. All right, so let's take a look at an example that uses the combined gas law equation. Now, sometimes they'll incorporate this partial pressure stuff that we just did, and sometimes they won't. It all depends if the example that we're talking about has over water as part of the question, or if it doesn't have over water as part of the question. So if it is over water, we're going to have to somehow take account of that using this equation. But if there's no mention of over water, then we just leave it the way it is and we deal with the problem as we see it. So we've got this problem here, and when we've got a situation where we've got two sets of conditions, then what we're dealing with is the combined gas law, where we've got P1V1 and T1 and P2V2 and T2. So what I like to do is write these out, P1V1 and T1 and P2V2 and T2, and then fill them in as we go. So being a word problem, this is what people really don't like, is having to figure out, well, what goes where. Well, the thing is, what you've got to do with the word problem here is make sure you're grouping the different pieces. the different conditions in the right places. So we've got P1, V1, and T1. It's going to be one set of conditions. And P2, V2, and T2, that's going to be another set of conditions. The key word here is actually a very small word, and it's the word at, because that word at allows us to group the different conditions together. So if you're looking to calculate the volume of a gas at a certain temperature and pressure, sorry, a certain pressure and volume, a certain pressure, and we've got a temperature here, then you can just use the at here. It says calculate the volume of a gas at 780.0 torr. So I know the volume I want is at that specific pressure. So I'm going to put a question mark on the volume because that's what we're looking for. And it's at a specific pressure, which is 780.0 torr. So there's our first set of conditions there. The temperature we'll get in a second, but it says if 500.0 mils is collected at 30 degrees Celsius and 730.0 torr. So all of those things are together. We have a volume, we have a temperature, and we have a pressure. That's going to be our P1, V1, and T1. Usually telling those apart is not too difficult. The volume is usually in milliliters or liters, but usually milliliters. Pressure is could be in atmospheres. Oops, should be 730.0 torr. You'll notice that I don't need to take account of the vapor pressure of water here because there's no mention of over water anywhere here. 730.0 torr, and then the temperature is 30 degrees Celsius. Now the temperature has to be in Kelvin. Now the reason for that is if you look at the equation here, P1 V1 over T1 equals P2 V2 over T2, you can see T1 and T2 are on the bottom, and there's no way that they could ever be zero. So we have to have them in a unit that can never reach a zero, and that would be Kelvin. The way we get any Kelvin temperature, of course, would be to add. So K is going to equal C plus, I'll put in 273.15. But notice that if we've got 30 degrees Celsius, this is going to go by the number of places past the decimal. You can see that the number of the 0.15 really won't matter anyway, and it just comes out to be 303 Kelvin. It says here the temperature remaining constant. All that means is the temperatures are going to match on each side. So that's how we set up the equation. But the key is looking at the at, where the ats are. That tells you what is grouped together and what you need to be looking for. Does anybody have any questions so far? That's not the end of the problem, of course. We need to solve for it now. So P1 V1 over T1 equals P2 V2 over T2. Now, since we've already got our data down here, we know what we're looking for, and that happens to be V2. So one trick that we can use is just a simple algebraic isolation. But one thing we can do is if we're going to divide both sides by P2 and multiply both sides by T2, effectively what that means is we're taking P2 and putting it on the bottom, and taking T2 and putting it on top. So V2 is then going to be P1 V1 T2 over P2 T1. Of course, these can be in any order on top and bottom. It could be T1, P2, that'd be fine as well. In any case, though, you can see what's happened is whatever's on the top on one side goes to the bottom on the other side. Whatever's on the bottom goes to the top on the other side. And really all we're doing there is dividing both sides by P2 and multiplying both sides. Sorry, dividing both sides by P2 and multiplying both sides by T2. then it's just plug and chug from that point. So P1. Now, you've got to be a little bit careful here. You've got to make sure that the units match on the pressures and the volumes and the temperatures. And then it usually matters more on the pressures, because that possibly could be in atmospheres, which means you might need to do a conversion on occasion. So let's see, P1, that's 730.0 torr. I'll put in all the units here because that's what I would usually do. Times the volume. The volume V1 is 500.0 mils. And the temperature here is T2, 303K. You'll notice they're the same. They're going to end up cancelling out. But let's see, we've got P2, that's 780.0 torr. Again, times the temperature T2, which is 303K. So you can see that what's going to happen is the Ks will cancel, the torrs will cancel, and we'll be left with the milliliters. And this is why I like to put the units in when I do this. So this would come out to be, it looks like 468 milliliters. I'm not going to go through all of these in this way. I'm just showing you this one fully worked, especially so I could show you the isolation step, how we isolate the V2 here. Does anybody have any questions? Okay.
I have a question.
Yeah. Mm-hmm.
So I'm looking at the module 11 assignment right now, and one of the questions is asking about finding a gas, finding out the identity of a gas with a specific grams per moles or density. And I was wondering what the best way to do that is, if you were to come up with like an example version of that, because I don't really see that sort of question in the soft chalk.
Yeah, well, we did do this one earlier. You were here, David. I know you were here at the beginning. But it's like this question here.
Oh, okay. Yeah, okay.
All right. So all you have to do is take the density and multiply it by the molar volume of a gas and see which one of those matches.
Okay. And you could also
You see that?
if you get the amount of moles, you could also use that on the periodic table with all the different gases.
Oh, I don't know, I suppose, but I think this would be easier. So because the molecular weight is going to just be the density multiplied by the molar volume of a gas at STP, which is, we already know, is 22.414. See which one matches.
All right, well, that's good.
Is that okay?
Yeah, that works.
Okay. Okay, let's see. All right, let's say we were solving for temperature. What would we have to do with that? So again, this is a good example of how we sort of sort out what's grouped together here. You'll notice though that pretty much all the time, all the stuff we need for each position or condition is usually going to be together. So if you've got here a gas, 100.0 mils has a pressure of 750.0 millimeters of mercury at 25 degrees Celsius. Remember, a millimeter of mercury and torr are the same unit. So you can see all of those things are going to be together. I'm going to go ahead and put them in. I'll just make sure I'm consistent. Remember, this could go either way, P1V1 or T1, or P2V2 and T2. But you'll notice what I've chosen to do here is leave T2 as being my mystery temperature. So that means that the first set of conditions, I'm just going to put in P1, V1, and T1. Now on any test, you're always told what the mystery temperature or volume or pressure is going to be, so you can always work your way around what I've told you there. So we've got P1 750.0 millimeters of mercury. Now you'll notice again there's no mention of over water here, so we don't use that vapor pressure I talked about earlier. The volume 100.0 mils at that specific. David, I'm going to ask you to mute, please, if you don't mind. And the temperature,
Yeah, sorry.
298 K. And again, I get that by adding 273.15. So there's my pressure, volume, and temperature one, P1, V1, and T1. The thing we're looking for is the new temperature. So I'll put a question mark there at T2. And it's a specific volume, which is 200.0 mils. And a specific pressure, which is 780.0 millimeters of mercury. So again, you'll notice that the units all match on everything that we know we have, which is good. So we have our equation here, sorry about that. P1 V1 over T1 equals P2 V2 over T2. And what we're looking for is T2. So this is a little bit more difficult to isolate. Now, you know that we could take the T2 over the other side and then take the other ones down. I think what's easiest when you're looking for a temperature, go ahead and flip both of them. Because what you do to one side, you can always do to the other side. So we can flip these two. And then simply take the P2 and the V2 to the top. So T1, P2, V2 over P1, V1. And that will equal our T2 value. And then we can plug everything in just like we did earlier in the previous one. And this will give us a Kelvin temperature, of course, because we've got a Kelvin temperature here as part of T1. Everything else will cancel, and we would be left with 620.K. Now, if you want to take a look at the actual equation here, and you look at the conditions, you can see that the gas is at 100.0 mils, 750.0 torr, and the temperature is 25 degrees Celsius, which we came out to be 298 K. Now you'll notice that the volume is changed to 200.0 mils, so the volume's gone up. Also, the pressure has gone up. So it makes sense that whatever temperature we end up getting here under those conditions will also be greater as well, with the pressure having gone up and the volume having gone up as well. And you can see the temperature now is 620 K when initially it was 298 K. So it's almost doubled. Well, it's more than doubled. Does anybody have any questions? Okay. So again, notice there was no mention of over water here, so we didn't have to worry about that. Now you'll notice in this example, example 6, we do have over water mentioned here, which means we are going to have to take account of water in our, the pressure of water in our calculations. So what we're looking for here, and this one is a little tricky, but again, the at is what helps us out the most here. We're looking for a volume. And as I have in the, as I've done in the assignments and everything else that we're looking at, the volume here is going, the V2 is going to be what we're looking for. So I'm going to put a question mark here. As V2. So look what it says here. It says calculate the volume of a gas at STP. Now what is STP? STP, I'll write down here, is standard temperature and pressure. So it's 1 atmosphere, which is also equal to 760 millimeters of mercury. Or torr, same thing, at 273 Kelvin or 0 degrees Celsius. So that's what STP always is. It's always standard temperature, standard pressure, which is 760 millimeters of mercury, 1 atmosphere, at 273 Kelvin or 0 degrees Celsius, which is the same thing again as well. But look at what the question says. It says calculate the volume of a gas at STP. So volume is what we want, but it's at STP. So we know what the pressure is. It's going to be, I'm going to write 760 torr here. And the temperature is 273 Kelvin. Now the reason I chose torr as the unit is because the other pressure is in torr over here as well. So I know that's going to match. That's the worst part of the problem done right there, because now I know what conditions I'm looking for to get the volume of the gas, and it's going to have to be at STP. And again, the most important word here is at, because I'm looking for the volume at STP. Does anybody have any questions? A lot of times when people see STP, they mix up where the units go and where the numbers go. Okay. So we do have over water here, so we are going to have to take account of the vapor pressure of water. So it's going to be 730.0 torr. And that's going to be minus the vapor pressure of water, which is going to be, and need that table, which I've got back on page, whoops. I've got the table here back on a previous page, so I'll go back there. So we're looking for the vapor pressure at 30 degrees Celsius, which is 31.8 millimeters of mercury. So that's what goes in here is minus 31.8 millimeters of mercury. This is to take account of the vapor pressure of water. I'm just going to use torr because torr and millimeters of mercury is the same thing. And as you can see, once we account for significant figures, we get 698.2. Torr. And then we got our volume, which is going to be, back to the question, if 500.0 mils. So that's what goes in volume 1 here. And the temperature is at 30 degrees, which we already figured out. So it's 303 K right there. So again, we've got our P1 V1 over T1. We've got our P2 V2 over T2. And again, we can isolate our V2, which is what we want. And we can just substitute all those values in. making sure that for P1 we put in our calculated value for the vapor pressure that takes into account the vapor pressure of water. So you'll notice that in the previous examples, we didn't do this subtraction part where we subtracted out the water. And the reason for that is because there was no mention in those examples of anything being over water. But once something is over water, then we need to subtract out the vapor pressure of the water from the pressure that we have in the problem. Does anybody have any questions? Okay, you sure? Nobody has any questions? We already did something like that. All right, and now we're going to move on to how we deal with situations where we are only given one set of conditions and we're looking for grams or moles. And that's when we employ PV equals nRT. So you might be wondering, well, when do you use P1V1 over T1 equals P2V2 over T2? And when do you use PV equals nRT? Well, the answer to that is that all of this is going to be two sets of conditions. So you'll usually have at least two of those things. So two sets of conditions. That's for P1V1 over T1 equals P2V2 over T2. And for PV equals nRT, it's just one set of conditions, but one of the giveaways is that there's usually mention of moles or grams. So moles or grams are going to be mentioned here somewhere in the problem. The assumption that we're making with the P1V1 over T1, the P2V2 over T2, is that it's a constant number of grams or moles of substance, and we're just changing the pressure, volume, and temperature, but we're not changing the moles. So that's why in those kinds of problems, you never see any real mention of grams or moles anywhere. The only exception to that would be when you're looking for the molecular weight of something, which I'll show you an example of that in a bit. So this one here is a fairly simplistic example, but when we're dealing with PV equals nRT, I think it's always a good idea to write down what you have. P equals, V equals, N equals, R equals, and T equals. Everything is going to revolve around our value of R, which is always going to be given to you, but it's a constant value. But what's equally important with the value is the units, and it's going to be liters, atmospheres per mole per Kelvin. And again, that's something that is always given to you as well. So liters, I'll put a little dot in here. Liters, atmospheres per mole per Kelvin is the unit on R. So everything we come up with here has to match those units: liters, atmospheres, moles, and kelvins. Now it says here how many moles are in 250 milliliter sample. So that would definitely be the volume, but the problem with that is that it's in milliliters and needs to be in liters. So I'll do a conversion here on the fly, times 1 liter over 1,000 mils. So that'll give us our volume there. I'll move this over here. Might have enough room here. 0.250 litres. The pressure, well, it says STP, so that's going to be, well, what unit are we going to use? We're going to use millimeters mercury, torr, or atmospheres. Well, we'll use atmospheres because we've got atmospheres in our R value. We're looking for N, which is number of moles. And the temperature, it says STP, so that's 0 degrees Celsius, but that has to be in Kelvin as well. So it's going to be 273 K. So you can see then it is just going to be a matter of solving for N. So PV equals nRT, N equals PV over RT. Again, I'll show you how this sets up so you can see how the units cancel. The pressure, 1 atmosphere, the volume, 0.250 litres, we put our R value in here, which again, I'm going to show all the units here, 0.08206. And it's litres, atmospheres per mole per Kelvin. And that's times the temperature, which is 273 K. So you can see the kelvins will end up cancelling. The moles will move to the top. The litres and atmospheres cancel. And that gives us our final answer here, which would be 0.0112 moles. Does anybody have any questions? Yeah, so the main focus should be on this R value here, because the R value will be telling you what units you need for everything else in the PV equals nRT equation. So pretty much all of them are handled that way. You can see in this one's not too difficult because you've got again, that volume is in milliliters, but that needs to be converted to liters, but you're given temperatures here, 298 K, and the pressure is in atmospheres, which is what you want it to be anyway. This one here doesn't even need any conversions. Neither does this one. Now, something like example 12, which I will go through. Oops.
I had a quick question
Yes,
about
David.
this is Rogers.
Oh, right. Sorry. Roland, what's up?
I just had a quick. So, like with the R, that's going to be given in the
Yes,
equation, or do you
absolutely.
have to look for a chart?
Yes.
Or do you have to look for a chart?
Nope. No, and I'll give you the number and the unit because the unit's really important.
Okay, and that's more of like a conversion thing, right? That's like the constant between the two. It's like
It
a
is.
ratio.
Yep.
Okay.
Mm-hmm.
Too easy. Thank you.
All right, so let's look at something like this one here. And we're again dealing with PV equals nRT because we know we've got moles, so that's kind of a giveaway. Again, I'll start out with R, which will always be given. We are looking for temperature, so I'll put a question mark here. We have moles. It's going to be N. we've got volume, which is 14.2 litres. Whoops. And we have a pressure, which is 766 torr. So here's an example of, we know we've got litres, which is fine, and moles, that's fine, because those match the units in R. But if you look at torr, torr doesn't match atmospheres. So we have to do a conversion for that. So it'd be 1 atmosphere times 1 atmosphere over 760 torr, which gives 1.01 atmospheres. And then we can go ahead and solve, because PV equals nRT. So T is equal to PV over nR. And we go ahead and we can come out to a temperature here, which is going to be in Kelvin, because that's the unit that we have on R here, and allows us to figure out that our unit on temperature would be Kelvin as well. But it's all just plug and chug from that point. But what I'm trying to do here is just really emphasize the fact that everything needs to match for units in R in order for you to be able to solve the problem correctly. Does anybody have any questions? So a related problem to this, and there's generally a couple of ways of doing this, but I'm going to show you what I believe is the easiest way. And that is to determine something's molecular weight given a mass and some other conditions here that allow you to find moles. Now, if you remember what molecular weight is, by definition, it's grams of something divided by or per mole of that substance. But it's always grams per mole. Now you'll notice that in the question we have grams already, so that's already figured out for us. What we don't have is the moles, but we do have a volume, a temperature, and a pressure, which means that we can use PV equals nRT to solve for those pesky moles that we're looking for. So Vn is the number of moles, so that we can figure out the molecular weight here. So the pressure we're given is 780 torr, which needs to be converted into atmospheres. Well, let's write down the R value first, make sure we're getting the right units. So you can see we have atmospheres here, but that doesn't match for torr. So we do that same conversion as we did earlier. 1 atmosphere over 760 torr, which comes out to be 1.03 atmospheres. The volume, 150.0 mils. And again, we're in that same situation. We need litres, so times 1 litre over 1,000 mils, which is going to come out to be 0.1500 litres. And the temperature, we're given 100 degrees Celsius, and that's going to come out to be 373 K. Again, goes by number of places past the decimal. So we do our PV equals nRT, and we're solving here for N, and then we're going to plug in all of those values, PV over RT, And we're going to end up, I'm not going to do the math here because you can see we did it earlier, 0.00505 moles is what we end up with for the N value. So once we've got that, then we can do our molecular weight. Which is going to be grams over moles. And the grams we were given in the problem, 1.324, I think it was. Let's go back. Yep. Divided by whatever we got for the moles, which is 0.00505 moles. And after all is said and done here, we end up with, I think it's 262 grams per mole. And that would be 3 significant figures. So this is a viable way for us to calculate the molecular weight of an unknown gas. If we had certain conditions, we would need the pressure. We need the pressure, the temperature, and the volume, and we'd also need the mass of the gas that we had. But if we had all of that, then we could find the molecular weight of the gas. Does anybody have any questions? Okay. So the last question here that we'll look at in Module 11 outlines what we would do if we were dealing with a stoichiometry case. So we can combine concepts that we learned in Module 9 and 10 with what we're seeing here in Module 11. Okay, so a 275 gram sample of calcium carbonate is decomposed under 1.25 atmospheres, 567 K, what volume of carbon dioxide gas would be produced? So you'll notice that we would always be given an equation here. You couldn't do it otherwise. But since we're dealing with gases here, we're only interested in how much CO2 we're getting. So it's going to be necessary first to determine how many moles of CO2 we're getting so that we can apply our PV equals nRT and come up with what we're looking for, which is a volume at the end. So the way this is, actually, I don't think I'll do this one. I'll just show it to you here. This won't be on the test you do, but it will be in the homework. So that's why I'm going to go through it here, but I'm not going to write it all down. I'm just going to show you the method. The important point is that we're starting with calcium carbonate, which is a solid, and you know it's a solid because it says S here. But what we're looking for is the volume of carbon dioxide. So we've got our PV equals nRT, but we need the volume, and it's going to be nRT over P, which means we already see we have a pressure, we have a temperature, we know we have R. What we need is the number of moles. We can get the number of moles by doing our flow chart here. If you'll remember our modified flow chart, QA goes to moles A, goes to moles B, goes to QB. Now what we're looking for in this case was we're starting with grams of calcium carbonate, which means we need to go to moles of calcium carbonate first. But that will then lead us to moles of CO2. And that's exactly what we do here. So we take the mass of calcium carbonate that we're given, we figure out the number of moles of calcium carbonate first by dividing by the molecular weight of calcium carbonate. That's 100.09 grams there. And the mole ratio here is 1 to 1. So it'd be 1 mole of CO2 over 1 mole of CaCO3. It's not always 1 to 1. It always depends on the equation you're given. And you're always given a balanced equation in these kinds of examples. So once we plug in all of that information that we have with the 2.75 moles of CO2 that we came up with, then we can calculate a volume of CO2 using all the other information we have. You'll notice that for an example such as this one, 175 grams of aluminum carbonate, I'll just do the first part of that. And what we're looking for again is the volume of carbon dioxide gas, CO2, produced. And you can see that the method there would be very similar. So 175 grams of Al2CO33 times 1 mole of Al2CO33 over the molecular weight of Al2CO33 times, in this case, it'll be 3 moles of CO2 to 1 mole of Al2CO33, which would allow us to get the moles of CO2, which could be plugged into the equation because we have all the other bits of information. All right, does anybody have any questions about that? So again, you won't see that on the test, but you will see it in the homework. All right, does anybody have any other questions? That's all of module 11, but there's still a little bit more stuff here that we have to look at. That's part of the test.
Could we look back at example 9? I found that one a little bit confusing.
Let me see if I can find that. Here we go. Okay. So, all right, what question did you have about that?
I don't know. I just kind of wanted to see you run back through the process again because I just didn't fully understand it.
So the key to any of these problems will always be to write down, well, first of all, to realize that you need PV equals nRT because you're looking for moles and you wouldn't be looking for moles under any other circumstance. Always write out the PV nRT. The R is always given. And the units are always given for R. Then we need to put in our information. The temperature is already in Kelvin, so I don't need to do any conversions there, that's fine. The pressure is already in atmospheres. But the volume is not in liters, it's in milliliters, so we need to do a conversion to make that into liters. So now the liters match over here. So then we can solve for N, which is what we're looking for. And N would be PV over RT. And all the units will end up cancelling to leave us with moles. So that's the basic method. That's for all of them, David. You always got to make sure that everything matches the units in R.
It's just about rearranging, in other words.
Yeah.
Okay, I get it.
Okay. Any other questions about Module 11? And most of the stuff we're dealing with was in the survival guide or in the soft chalks, but there's some stuff here that isn't. And an example is about diffusion, diffusion of gases. I don't talk about that in Intro to Chemistry, but it is part of the curriculum for General Chemistry 1. So this is a good place to put it. Let's see. Let me see where this goes. Yeah, okay. So this talks about diffusion of gases. So I'm going to, let me see, let's do a new share here. Share computer sound. All right. And you can see an example. This is a really good example of what happens with diffusion of gases. I'll move this down here.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on the cotton in the tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. The rate at which the gas travels down the tube is dependent upon the molar mass of the gases.
So we've got HCl. So HCl over here, we've got NH3 over here. Now those are solutions, but they're going to let off a gas that runs through the tube. Now HCl, if you look at the mass of it, is going to be 1 plus 35. It's about 36 grams per mole. The NH3 is about 17 grams per mole. So what's going to happen is, as we talked about earlier, smaller molecules move faster. So the NH3 will diffuse down to this point, and the HCl will only get over to here. So if you look at where the product ends up, it ends up at about halfway point, well, sorry, the 1/3 point here, closer to the HCl than to the NH3.
When the gases come together, they react to form solid ammonium chloride, which forms a white solid in the tube. We see that the white solid is closer to the HCl side than the ammonia side. This is because the ammonia has a lower molar mass and diffuses faster than the HCl.
Yeah, so fairly simple there. That's what the concept is. Oh gosh, I didn't mean to. Sorry, I didn't mean to get out of my courses there. I thought I'd open up a new tab, but I wasn't. Okay. I'll make sure it does in the future. There we go. So we can also talk about, so that's basically diffusion there. It's also just another illustration of the importance of what happens when we have smaller differences in molecular weights of the gases. Smaller ones move faster. So there's another concept we can talk about called effusion. So this is diffusion that we just talked about. Effusion is a little bit different. Effusion is the passage of a gas through a pinhole into an evacuated chamber. Now, a similar concept applies here. Lighter gases will tend to travel more through the pinhole than heavier gases will. But we talk about Graham's law as being the rate of effusion of gas 1 divided by the rate of effusion of gas 2. So we can look at this ratio here of the effusion of gases. The equation that relates these rates of effusion is going to be molecular weight of gas 2 divided by molecular weight of gas 1. Notice how it flips around. Again, it's that inverse relationship between speed and size. The fastest, the smaller something is, the faster it goes. So it makes sense that these are flipped around. And you'll notice it's the square root of that ratio of the molecular weights that we end up with. So one of the applications of this is the separation of uranium-235 from uranium-238. So the uranium-235, that's a fissionable one. Uranium-238 is not as fissionable. So the more uranium-235 you have, the more fissionable your material is. So this is the one that's used in nuclear reactors and sometimes in nuclear weapons as well. A lot of it's 235. So you can theoretically, well, actually not theoretically, practically, you can separate U-235 from U-238 by using this rate of effusion. So what happens is the lighter one, the U-235, effuses more than the 238. So this is used to enrich uranium with U-235, and this is a picture of an enrichment facility in Paducah, Kentucky. It's a big facility because this has to be done lots of different times in order to enrich the uranium. So it has to be the mixture of U-238 and U-235 has to go through all of these different pinholes into evacuated chambers. And each time it does this, the enrichment process has more U-235 than U-238 as we go through. But it takes a lot of room to do that. In Iran, they don't use this technique. They use centrifuges to separate the U-235 and U-238 and to enrich it. So you might have heard about that in the news, about having to destroy or disable centrifuges that were allowing them to enrich uranium-235. Enrich uranium with 235. So let's look at an example of that. So I'll pull this up. This is on the test, so I'll go through this. Let's see, test 2. Okay, let's see if we can find that question. Here we go. What's the ratio of rates of effusion gas 1 to gas 2? And here you're given the molecular weights. Oh, come on. And the formula that you're going to be using will be the Graham's law formula to solve this. So it'll be rate of it's looking for gas 1 to gas 2, so that's important. We need to know what we're looking for here. So rate of gas 1 to rate of gas 2 equals the square root of the molecular weight whoops, of gas 2 over the molecular weight of gas 1. So it's important to note that it flips because of that inverse relationship I was talking about earlier. And you know, you can see that you're given the molecular weights here, 88.27 and 85.76. Over 88.27. So gas 2 over gas 1, take the square root, and that gives you the fusion ratio right there. And what I would be expecting is something less than 1, since gas 1 is heavier than gas 2. And if gas 2 was happened to be heavier, then I would expect, again, the ratio to be greater than 1. So that's pretty much all there is to that kind of problem. Yeah, and it will be on the test. You can see it's question 17. All right, so we'll leave it there for today. We'll do module 12 on Wednesday. There'll be a little bit of time. We'll start our review then for the test. And then there'll be a review on Monday as well. Then there won't be class on Wednesday because, well, hopefully you've already taken the test by that time, but I leave Wednesday free to make sure everybody gets a chance to take the test. All right, so we'll leave it there. If anybody wants to ask any questions, you can hang around. Otherwise, I'll see the rest of you later. Bye. Thomas, Jordan, do you have any questions? Okay.